Hi, in this video we're starting on my favorite topic. I guess you shouldn't have favorites, but I quite like logarithms. So in this video we're going to look at what common logs are. We'll also look at natural logs. We're also going to look at how to convert from exponential form to logarithmic form. We'll do some changing of bases, just quick graphing, transformation of logarithmic graphs. And then at the end, we'll solve a pH question. Just before we go on, this picture, quite like this one, is a picture heading downstream on the Old Man River around Tabor, a place where not many people go at all on this side of the river. Okay, so in the last section, I sort of left you hanging. And today we're going to start uh, looking at how I can get you out of that hanging position. We asked a question like this one where we put a 1 in for that, and we had a 20 here, negative 0.8 t, and we had to solve for t. And we didn't have a way of doing that. So today we'll start looking at how you can get at a variable that's in the exponent. Now, logarithms are actually an inverse function of exponential function. So here the blue line, I think it's blue, yeah, this one right here that I'm making black, is an exponential function. And most exponential functions have that same shape. Well, logarithmic ones are inverses of that. And an inverse function, I won't go into in too much detail, but is where the x and the y values swap places. Graphically speaking, an inverse function is one that when you look at the graph, like this is the logarithmic graph, that one there, that they are reflections of each other across this middle line. So there's a middle line, y equals x right there. And so if I have a point here, then if I reflect across this line, I'll get an analogous point over on this side. I maybe should have come down a little bit. Anyway, there's a mirrored image over on this line, and they're inverse functions of each other. Just looking at a log graph, let me just put one up here. So y is equal to log. To do that, you have to get into that functions area, and I think it's under miscellaneous. There's log right there. And I can type log of whatever number, like, oh, let's put x in so we can see a graph. So there's a graph of y equals log of x. The transformation of log graphs is the same as transformation of all the other ones. This thing here will make things taller, or it'll stretch things vertically. Let me put a 2 in right there and watch what happens to the graph. All of the y values get multiplied by 2. If I were to take and put a minus 2 in right there, in the old graphs, that would shift things to the right 2. Let's see if that happens here. Minus 2. Sure enough, it gets moved to the right 2. And then finally, let's move things, do the plus 3. That should move things up 3. So plus 3, sure enough, moves the whole thing up 3. So log graphs, you need to know that general shape of them, like this, but the transformations are the same as what we've seen before. Okay, so now let's see what this log terminology or this log format looks like. So this is sort of a logarithmic equation right there. And basically what it says, the thing on a side by itself in log expressions is known as the exponent. This 2 at the bottom there is known as a base. And then this number here, well, let's call it a value. So when they ask you, when you're reading this, what you say is 2 is raised to the third exponent in order to get 8. Or you can say it this way and start backwards and say 3 is the exponent to which 2 is raised in order to get 8. See if you can read this one down here. So x is the exponent to which 3 is raised in order to get 9. It seems a little awkward, and we'll do an exercise here in a second where we can change it into an exponential form, and then maybe it makes a little bit more sense. But that's what each of those is saying. Let's just try one more. So if I say have log base 4 of x is equal to 3. So 3 is the exponent to which 4 is raised in order to get that value. Okay. So when we're simplifying these and when we're trying to find the value of them, you want to sort of keep that in your mind how to read it. So this is the exponent to which 10 is raised in order to get 100. Now you might think to yourself, well, what is x? So x is the exponent to which 10 is raised in order to get, so what exponents do you have to raise 10 to in order to get 100? Well, it's 2. And that would be the answer to that logarithmic equation. Same thing here. So to what exponent must you raise 3 in order to get 243? To what exponent must you raise 3 to get 243? I think it comes out to 5. Try that. On your calculator, just go 3 to the 5th, see what you come up with. Next question. Oh, this one. 4 is the exponent to which 3 is raised in order to get x. So 4 is the exponent to which 3 is raised. So 3 to the 4th, I could figure out what that is. I think that comes out to 81. Okay, you sort of getting the idea of how to read those log equations. This is something that will help. And just memorize how you can change from a log form to an exponential form, or going opposite way. Now, I've color-coded these things to help you, so you sort of know where all the bouncing numbers wind up. The key thing that I look at is the bases. Notice the base there in that logarithmic expression is the same as the base of the exponential equation. So I always focus on that first. So for example, for this one, if I wanted to change that to exponential form, that's where I'd focus first. So 1.05 to the, and this thing, a logarithmic expression, is always equal to an exponent. So that becomes the exponent is equal to the other number, which would be a 2. Let me try this one. So 2 is the base. This thing on the other side's got to be the exponent, is equal to 8. Oh, now let's go backwards. Okay, so here I've got an exponential form. Let's go to log form. So there has to be a log in it. This is the base of the exponent. It becomes the base of the log. And make sure when you're writing it as a base, you write it down below and small, so it doesn't look like it's just a regular number. So that's the base, and the exponent is what things are equal to, so that's x, and so the 125 has to slot in right there. Let's do the next one. So log, the base is x, of 27 is equal to the exponent right there. Why don't you try some? Go ahead and do those, press pause, then play, see how you do. First one, 2 to the 4th is equal to x. Next one, 6 to the x is equal to 216. We'll solve these two later, but we're sort of working up to that. The next one, it'd be log base 3 of 81 is equal to x. Next one, log base 4 of 256 is equal to x. You want to get very good at switching from one form to the other form. A question or two on the test will be doing exactly this kind of thing. Okay, now we've seen a few different kinds of bases, and we have some special ones. On a normal scientific or graphing calculator, they have 2 log buttons. One of them is a common log, and that's the one where you have a base 10. So there's a base 10. And typically that's the common one. So usually we don't even write the base in. See, like in this one. So if they say what's the log of 50, and they don't put a base in, you assume that it's 10. So that's one of the types of log buttons that we have, and that's the common log. Another one that we use quite often is when you have a base e, and that's known as the natural log. So if you have a log with a base e of 10, rather than writing this log base e we have a short form for that, and that's just ln. Usually we pronounce that ln, so ln of 10 is what that would be. So that's the second type of base that you would see. Let's just try some of these on your calculator. Now, unfortunately, on your calculator, you don't have a base 5, but you do have a base 10, and you do have a base e. So why don't we start with those? So just on your calculator, just hit the log button, and then 25, and you should get 1 point something or other. Let me try it on decimals here. So in decimals, you have to hit the function button, and then I don't see any log there, so I think it's under miscellaneous. And here's a log button. Now notice that this one has 2 log buttons. There's a log and a log base A. So this log base A will let me do any base. I'll show you in a second how you can change base on your own, but this is a cool one. Let's just try the base 10 first. So I'm just going to hit the basic log, and I want to type log of 25. Whoops, 25. So see, it comes out to 1.4-ish about. So I'll call that one 1.4-ish. Let's try the next one. So I want to do ln of 50. So hit function. Oh, I'm already there. Ln of 50. 50. 3.91 about. 3.91. Now log base 5 of 25. Maybe I don't have to do that on my calculator, because what that's saying is, to what exponent must 5 be raised in order to get 25? So you could just sort of think that through. To what exponent is 5 raised to get 25? Well, the answer is 2, right? Because 5 squared is equal to 25. So that answer would just be 2. We can test it on decimals too, if we want. So log, let's do that fancy log button. So this log with an A on it, that's a good one. So the A, that's our base, would be 5, and then we're taking the log of 25. Whoops, 25. So that comes out to 2. Now the next question is log base 5 of 23. Let me backspace and just put a 3 in there. Log base 5 is 23. It's got to be just a little bit less than 2. And sure enough, 1.95, call it. Okay, so you should be able to use your calculator to solve for logarithmic expressions or equations like these. Now, if you don't have a log base A, or one that you can put your own base in, so for instance, this one here, log base 7 of 40, maybe you don't have that base 7 on your calculator, and we have base 10 and base E, but most calculators don't have any other base. But it's okay, there's something called the change of base formula. And what it says is, if you have to take the log of something where A isn't a 10 or an E, what you can do is just take the logarithm of any base you want, and we'd pick 10 or E, of Y, and divide it by the log of that same base of A. So in this one here, I could just say ln of Y divided by the ln of A, and that's going to come out to the same thing as this. But I don't have to use ln. I could use log base 10 of Y divided log base 10 of A. So for in this log base 7 of 50, now I know that answer is going to be 2 point something, because 7 squared is 49, and 50 is just a bit more than 49. So instead of 7 squared, it'd be 7 to the 2 point something or other. So I know the answer is 2 point something. But to figure it, if I don't have base 7 on my calculator, I could go ln of 50 divided by ln of 7. Or I could do log of 50, base 10, divided by log base 10 of 7. And both those answers should come out to be the same. Let me try them over here and just see if that works. Okay, so I'm saying, well, let's first do the fancy one. So log base A, so we're using base 7 of 50. Sure enough, it's 2.01. But let's try and use that to change a base formula. So we're going to do log, or let's use ln. There's ln of 50, close my bracket, divide, love how it shows a fraction there, ln again of 7, bracket. Notice it gives you the exact same number. And you could do log base 10 of 50, divide log base 10 of 7, same thing. Try that on the next question. Just see what you come up with. Try it on your calculator. So you could use the base A thing if you want, or you can say, well, that's the same as ln 512 over ln of 2. And you can do that. Okay, now logarithms and lns are all over the place. But just there's lots of examples where a population or amount of something changes based on how much stuff you have in it. Here's a good example, the pH of a solution. So pH of the solution is just an easy way or an easy number to give us an idea of how acidic or basic a solution is. The scale goes from, I think, from 0 to 14. 7 in the middle would be water, that'd be neutral. Anything on this side would be very acidic. On this side, it'll be fairly basic. So if I wanted to determine what the pH of a solution is that has this as the hydrogen ion concentration, here's the formula I can use. So the pH is equal to the negative log of 1.15 times 10 to the minus 6. And then I can just plug that into my calculator. Let me try it in decimals. In decimals, I don't think that I can do exponential notation. We haven't figured out how to do it yet, but I'll try my best. I think I can use decimals to figure this out. Okay, so I need to go negative, negative, and then log, here's my log, and it's base 10, so I'm just going to hit the log button, of 1.15 times 10 to the minus 6. I don't have that exponential notation that I figured out. I'm just going to write that as a decimal. So it'll be 0.00, I need 5 zeros, I think. 1, 4, 5, 1, 1, 5. There we go, bracket. Oh, I didn't get a 1, 1, 5 in. 1, 5. There we go. I'm finding with this, I often miss hitting a digit, so just be careful, always double check. There, so I've plugged that in. I think the decimal equivalent of the scientific notation is correct, and so the pH comes out to 5.939. So this pH would be 5.939. And there's no units associated with pH, so it's just 5.9. So this solution would be slightly basic, 5.939. Now here's another question where you've got to figure out, this time, the concentration of a solution that has pH of 6.82. So if I plug the number in here, 6.82 is equal to negative log of hydrogen ion concentration. This time I'm trying to solve for this, and I know that what the pH is. So this is one where it really comes in handy, and we're just bordering on getting into solving equations. It comes in handy knowing how to change from one form to another form. Let me show you. There's no log bit written, and so I assume that that's base 10. So what I need to do is isolate this piece, and so I'll divide both sides by -1. So I'll come up with negative 6.82 is equal to log base 10 of the hydrogen ion concentration. Now change this from log form to exponential form. Remember that we focus on the base, so there's our base. So base is 10 to the negative 6.82 is equal to the hydrogen ion concentration. There we go. So now I just have to put this into my calculator and see what I come up with. Let's try our old decimals again. You can tell I quite like decimals these days. Okay, so I've got 10 to the AB button, negative 6.82. There we go. So my answer is the hydrogen ion concentration is equal to 1.51. Oh, I think it'd just be 1.5 times 10 to the minus 7 moles per liter. All right, why don't you try a couple? There I've given you a pH and a hydrogen ion concentration. See if you can determine, fill in the blank for the other one. Press pause, then press play. I'll do the second one first. So pH is equal to negative log of the hydrogen ion concentration. So it's negative log of 5.11 times 10 to the minus 5. So you just plug that into your calculator, see what you come up with. For the other one, it would be same formula, hydrogen ion, but I need to put a 2.43 in here, equals negative log hydrogen ion concentration. Move the negative over, so I get this is equal to log, remember it's base 10, of the hydrogen ion concentration. Then change it from log form to exponential form. So the base is 10, so it'll be 10 to the negative 2.43 is equal to the hydrogen ion concentration. And then just work that on your calculator. Okay, so this section we have done an introduction to logarithms. We've sort of defined what they are. They're inverse functions to exponential ones. We've seen how you can change from exponential to logarithmic form. We've used the change base formula. We did that last applied problem with pH, and there's lots of other examples of those. And initially, we also looked just quickly at the transformation of log graphs. Okay, go ahead and try to do the video quiz and the homework and the other quiz. If there's any questions that you have, please let me know.